Hey guys, welcome to the second lecture in the methods series. We're going to talk about measures and data. So when we talk about measures and methods in cognitive science and neuroscience, we're talking about the scientific method, obviously, so we need to know the difference between science and not science. So real quick, because I'm sure you guys have a basic understanding of this, science is empirical. It uses observation to gather knowledge about the world. Science is not intuition, it's not common sense, it's not folk wisdom. So an example of a good application of science, way back in the day, scientists used to believe that combustible objects would release this element called phlogiston when they would burn. Okay, so Antoine Lavoisier, fancy name, fashioned this contraption here and showed that if you burn metal here, yes, when burned, metals don't get any lighter, right? So they're not losing anything. They're not burning off any kind of elements because their weight doesn't change, right? Excellent application of the scientific method. If you have a question, design an experiment to answer that question. When you don't, we often end up in the kinds of situations that we end up with the Monty Hall problem. So how do we avoid ending up in these situations? We go with the scientific method, just like Mr. Fancy Pants Lavoisier. So, Occam's razor. This is a huge founding principle in the scientific method, or a huge, let's say, foundation of the scientific method. Occam was an English Franciscan friar, and he was actually advocating for divine intervention or miracles when he came up with the law of parsimony. And what it states is that the simplest explanation is often the best. So as he was advocating for miracles, right, it's way easier to explain the things that seem impossible by saying that it's a miracle than to scientifically investigate them, right? But when you apply this principle to science, it works, right? So the simplest explanation is often the best. So let's try this out. Let's go through the steps of the scientific method to see how we get to the easiest explanation, the simplest explanation. Okay, so here's a working hypothesis. All work and no play makes Jack a dull boy. Okay, that is our theory. So what are the steps of the scientific method? And I know most of you probably were introduced to this in 7th grade, but we're just going to have a quick review. Okay, so steps for the scientific method. We need to specify the problem. All right, so the problem, what's the problem? The problem is we have to define work, we have to define play, we have to define dull, and we kind of have to define all, right? So what does work mean? Because for some people, what qualifies as work is actually enjoyable to other people. What does play mean? Because the same situation here, right? What does all mean? When you say all work, do you mean all day? Do you mean all week? And what are we using to assess dull, right? Is there some kind of a questionnaire, a dullness questionnaire that we can use? Maybe we should go with that. All right, so we've defined everything in our statement here. Now we say, okay, we have these variables. Now we need to design an experiment to test our question. So we need things like reliable and valid measures. We'll talk about the specifics of those in a minute. We need quantifiable data. And we need a design that can be replicated. It can't be some crazy, this can only happen once in the lifetime of the universe type design. It has to be replicable. So let's say that you decide that a day is going to be 16 hours, right? Let's say you decide to vary the percentage of play to work. And then you decide to observe the outcome on a dullness survey. Okay? All right. So now you generate your hypotheses. Hypothesis is basically what we see above. Okay, we think that a higher proportion of work to play is going to result in a higher score on the dullness survey. Now we test it. Run through your design. Gather some data. Now you form theories based on what you found. Okay, so you say so we actually found that it's not an all or nothing situation. It's not all work and no play makes Jack a dull boy. So basically, it's anything less than 30% play in that 16-hour day results in significantly higher dullness ratings. But that's only when he does it for 3 or more days. So now we say, here are the results, and here's our new hypothesis. Over 60% work in a day makes Jack significantly duller, but only if he does this for more than 3 days. Okay, so we've revised our hypothesis. Now we have to replicate. We have to test it again. So when we do this, we want to use new populations. Let's not use all the Jacks of the world. Let's use all the Jills of the world. Okay, so does all work and no play make Jill a dull gal, right? Does all work and no exercise make Jill a dull gal or Jack a dull boy? And what happens if we vary our design? So maybe we don't use a dullness questionnaire to measure our outcome. Maybe we use something like sleepiness. Maybe sleepiness is going to be used to indicate how dull a person is, right? Okay, so that's how we get at a simple answer when we have a question according to the scientific method. But I want to zoom in a little bit on what we call reliable and valid measures. So, measures. What is validity? Validity is, does it measure what it's supposed to measure? So, if I want to know how tall you are, putting you on a scale isn't going to be a valid measure of your height. Okay, it's a valid measure of weight, but probably measuring you with a tape measure is going to be a valid measure of height. What about reliability? Are the results consistent? So if I test you over and over and over, just you, the same way, over and over and over, am I going to, on average, because there is variation from trial to trial, right? If I test you over and over, on average, am I going to get consistent results? Okay, that's an internal reliability. An external reliability is going to be more about, okay, if I do the same thing that I did for you, if I do that on everyone else in the world, am I going to get the same kinds of results? And the last thing when we talk about good measures is power. I know I didn't mention this before, but you need to have a powerful design, a design that is going to be able to capture the effect that you're looking for. Let me explain. Let's say that effect size is actually analogous to diamond size. Okay, now you're standing in a room and there's 50 other people in this room. You have a diamond and you lose this diamond and you need people to help you find it. If the diamond that you lost is the size of a baseball, you're not going to need a whole lot of people to help you find it. It's pretty easy to spot. If the diamond that you lost is teeny, teeny, tiny, you're probably going to need those 50 people and more to help you figure out where that diamond is. This is the same kind of thing when we're designing a research study. You want to make sure that the measures that you're using to detect whatever it is that you're looking for are going to be strong enough to detect it if in fact it is there. Okay? All right, so now let's talk about quantifiable data. What's in the numbers when we get data and what do we want to look for? So there are two big types of data. Descriptive and correlational. Descriptive are used a lot in science. Correlational are used, but you have to be careful with them, and we'll talk about this. We'll talk about why in just a minute. Okay, so descriptive statistics. We talk about we talk about numbers that tell us about central tendency. So where do most of our scores fall? How does our distribution of scores look? Okay. We also talk about variability, how the scores differ from one another. Okay, so When we work with descriptive stats, we want the statistics to describe what we call frequency distributions. Okay, these are two frequency distributions, one for women and one for men. Okay, and these are their scores on a fine motor skills test. Okay, so this is a hypothetical group of men and women and hypothetical test of fine motor skills and their scores on it. Okay, so descriptive statistics are going to help us sort of build in our mind the frequency distribution. Now you can actually build it on paper too, as we've done here, but when you read descriptive statistics, if you understand what they mean, you can get a rough idea of what the distributions look like. Okay, so let's talk about central tendency measures. Central tendency, this is stuff that you've heard before, I guarantee it. We're talking about the mean, what's the average of all these measurements. Here it's 3.27 because if you add all of these scores together and divide by the number of people, which is 15, that's your mean. Median is the middle value. Here there's a middle value in 3 because there are 10 scores that are equal to or greater than 3 and 10 scores that are equal to or less than 3. And then we have the mode, which is the most frequently observed measurement, which is also 3, right? There are 1, 2, 3, 4, 5 people that got a score of 3. Now, the reason why these scores can tell us about what our distribution looks like is because when these scores change, the shape of the distribution changes, or vice versa. When the shape of the distribution changes, you're going to have different scores. So in a normal distribution, which is also called a bell curve, we have the mean, median, and mode are all the same thing. Okay, and you can see why by the shape of this graph. And the shape of this graph is what we want to get, say, like when I administer an exam to a class, I want to make sure that my test scores come out looking like this, because it means that the test wasn't too easy, it wasn't too difficult, it was a good assessment of what the students as a whole were able to learn. Okay. When you have a positively skewed distribution, now your mean, median, and mode changes, because now your most occurring score is lower than the mean. Okay, when I have a positively skewed distribution like this, when I've given a test, I know that the test was too hard. Why? Because most of my scores are low. And, it's the opposite for a negatively skewed distribution. Most of the scores are going to be high. I know that this test was probably too easy, but I also know that y'all are sitting there with big smiles on your faces, which kind of makes me happy. Okay. Right, so this is just an example of how these scores can really tell us about what our frequency distributions are doing. So let's talk about variability. When we talk about variability, really what we're talking about, in a sense, is range. So if you look at the range of the men's distribution here, the lowest score is probably around 70, the highest being around 130. That's when you subtract 70 from 130, that's going to be a bigger number than what you get when you take the range for the women's distribution, right? So the men have a larger range of values. Standard deviation is all about the average distance between each of these measurements and the mean of the distribution. So on average, how far were people off from the mean? How much did people vary from the mean? All right. Now, when we talk about correlational data, this is where things get tricky, and you have to keep some things in mind. Correlational data is all about changes in one variable being accompanied by changes in another. So when variable X does something, variable Y does something else. And this is a consistent relationship. Just as a reminder, even though we've said the word a million times in this lecture already, a variable is a property whose value can vary across individuals or over time. So as a group, as a class, I could assign a variable of height to my class. And I know that over time, height changes for most people. Not so much for me because I'm pretty short. Okay. So when we talk about correlational data, we have positive correlations. So as you get older, your weight increases and your height increases. We have negative correlations. As you get older, right? This is age here. As you get older, your health So, okay, this chart is backwards and it always trips me up in the lectures. Okay, so age is higher up here, health is better down here. So as you get older, your health gets worse. Okay? As you get younger, which we don't get younger, your health gets better. All right, and then there's zero correlation, where basically there is no relationship between height and aggressiveness, right? Short people aren't all mean, okay? All right. When we have correlations, we can actually quantify the strength of these correlations. So we can say, basically, when you have a really strong correlation like this, right? If you had a perfect correlation of 1, you would have basically a straight diagonal line right across this chart here. Now this is a really strong correlation because you can see how much these dots would be hovering right around that trend line. This is a little bit weaker still, and then we've got no correlation down here. Okay, so the more these data points cluster around a trend, the stronger the correlation is going to be. Now let's talk about where correlations can really get you. So let's say that I tell you that people that eat more ice cream are more susceptible to sunburn. Okay. What I've left out is that ice cream consumption goes up in the summer, and so does the likelihood of sunburn. So it's not that ice cream consumption has led to an increased likelihood of sunburn. It's that the summer months have led to an increase in both, right? So that's a confound variable. You can't talk about the relationship between ice cream and sunburn because there is none. The only reason that they're linked is because of summer. So the big thing to keep in mind is the difference between correlation and causation. Ice cream consumption does not cause increased susceptibility to sunburn, right? Just like 100% of people who breathe die, right? Breathing is not the direct cause of death. But not breathing, 100% of people who don't breathe die. Not breathing, in that case, would be the direct cause of death. This is a causation statement, and this is a statement of correlation. Hopefully that makes it a little bit more clear. All right. Here's another example of a confound variable. Children that are exposed to a lot of media violence, and we've all heard this one, tend to be more aggressive. Okay, so maybe the relationship is that an increase in exposure to violence leads to more aggression. Maybe it's more aggressive kids watch more aggressive TV. Who knows? But we know that they're related, right? Well, we also have to consider adult supervision. So, yes, kids that are exposed to media violence do become more aggressive. But that's under the assumption that they suffer from a lack of adult supervision. Because children that are properly and adequately supervised, but still exposed to media violence, tend to not become as aggressive or aggressive at all. Okay? So, important things to remember with correlations. Correlation does not imply causation, and you've probably heard that before, and you'll probably hear it again. It's a very important principle to keep in mind when you're talking about statistics, and it's important when you're watching TV. Marketing, they love to play on this. They love to play on the fact that a lot of people don't understand the difference between correlation and causation. So, how do we get at causation instead of just getting at correlations? To do that, you're going to need an experimental design, and we'll talk about experimental design in the next lecture. So, I'll see you guys there.